Organic Chemistry 1. This is Chapter 4, which deals with alkanes and cycloalkanes. Alkanes and cycloalkanes. So an alkane is a hydrocarbon, which means nothing more than it's a molecule composed of only two elements, right? You can think about hydro, which represents hydrogen, and then carbon, well, you can probably guess that represents carbon. So molecules that are made of only hydrogen and carbon, we call those alkanes. There are other types of hydrocarbons that aren't alkanes. For example, an alkene or an alkyne or an aromatic. Those are all hydrocarbons as well. But again, our focus in this class is going to be on alkanes. So you can see that a hydrocarbon can be what's called saturated or unsaturated. All saturated means, and you see that only ethane, out of all the four molecules shown in this slide, only ethane is a saturated hydrocarbon. That's just another way of saying that in the ethane molecule, there are two carbons, and it has the maximum amount of hydrogens that are possible per carbon atom. So two carbon atoms, when you have two carbon atoms, the maximum number of hydrogens that you could have follows this formula, which is CnH2n plus 6, or sorry, 2n plus 2. I got 6 on the brain here. So if I have two carbons, right, 2 times 2 is 4, plus 2 gives you 6. So the maximum number of hydrogens you could have is 6. And you can see that ethylene, acetylene, and benzene all have less than 6 hydrogens, and therefore we say they are unsaturated. They do not have the maximum number of hydrogens that are possible. So alkanes, saturated hydrocarbons. How do we name an alkane? Well, what's interesting about organic compounds is lots of organic compounds just have common names that came, that have, I'd say, historical significance. They're just named, for whatever people chose to name them for. If you look at these examples that are shown here, and these come straight out of the book, they're just some interesting examples. For example, formic acid, it's the simplest possible carboxylic acid. It's named after the Latin word for ant, which is formica or formica. I'm not sure how to pronounce it. I don't speak Latin very well. But the defense spray that some ants release has formic acid in it. Urea, for example, you can probably guess where urea comes from. I told you it was the first organic compound ever synthesized from non-organic or inorganic starting materials. It comes from urine. Morphine, if you've ever wondered, I'm sure that you've all heard of morphine. Morphine is a very powerful painkiller, but it's named after the god of dreams, Morpheus. And barbituric acid is a really funny one because Bayer, or Adolf von Baer, he named that after a woman that it says in honor of a woman named Barbara. I always heard that he was infatuated with this woman, so he was like, I will name an organic compound after you. So that's kind of an interesting one there. And if you've ever heard of the type of illegal drugs that are referred to as barbiturates, they would be related to this kind of structure here. Well, what if we want to name an alkane? What kind of rules do we follow if we want to name an alkane? Well, first of all, we're going to talk about the Iupac system, which is just the systematic way of naming compounds. So what's great about Iupac nomenclature is that it allows scientists to communicate with one another all across this planet, right? If you're a scientist, and it doesn't matter if you're working in Florida or Ethiopia or, Japan, or if you're in, Kazakhstan, all scientists in those countries can communicate with each other because they're going to use the same nomenclature system to name compounds. So first it says identify the parent chain. So that means you've just got to find the longest string of consecutive carbons. How do you find that? You use a skill that I call T&E, trial and error, and I'm not kidding. That's how you do it. You just keep looking until you find it. I don't know if any of you had Dr. Diaz as an instructor at any point at UCCS, but he loves to ask these kind of questions like, hey, can you find the longest carbon chain in this molecule, this big molecule or something? So, if you were to take this molecule and say, okay, I'm going to find the longest carbon chain, you might be tempted to say, well, if I go 1, 2, 3, 4, 5, 6, 7, that's a lot of carbons, but that's not the longest chain. What if you did 1, 2, 3, 4, 5, 6, 7, 8? Hey, that's even more carbons, but it's not the longest chain, is it? Right? You could even do 1, 2, 3, and you'd really be way off in left field. But anyhow, you can see that the longest chain has what? 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So again, trial and error. You've really got to just look at the molecule and you're like, that's how you do it, trial and error? Yes, that's how you do it. You just look at the molecule and keep trying until you're 100% sure that you found the longest chain. Let me tell you one more thing about the longest chain. If you have, like, let's say this chain here, this molecule has 9 carbons. Let's say you had a molecule that had two 9-carbon chains and they were a little bit different. In that case, if you're wondering, well, how would I differentiate between the two? You want to find the longest consecutive chain of carbons that has the most branches. The most branches. I can't spell. There you go. And anything that's not part of the main chain, like that's a branch, this is a branch, this is a branch, this is a branch. So again, if you had that kind of situation where there was a tie in terms of the longest carbon chain, you would take the one that has the longest carbon, or the most branches. Now, in terms of these parent chains, right? What if your parent chain has 9 carbons like this? What if it has 8 carbons? What if it's got 10 carbons? What if it's got 4 carbons? How do you name those? Well, you've got to memorize table 4.1. And what I want you to memorize are the first 10, and I think it's also wise to memorize 11 and 12 as well. They don't come up as much, but they do come up from time to time. So if you have only 1 carbon, that would be CH4, that's methane, right? And I'm not going to draw this, condensed structure for everything here. But if you have ethane, that's when you have 2 carbons in a row, ethane. And then from there, you go to propane, and you can see I'm running out of space here, aren't I? You go from propane to 4 carbons, which is butane, 5 is pentane, 6 carbons, hexane, heptane, which is 7 carbons, octane for 8 carbons, nonane for 9 carbons, decane for 10, 11 is undecane, and 12 is dodecane. So you have to have that memorized. Methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, undecane, and dodecane. Those are going to come in really handy. And now you can say, to your friends, like, what in the hectane, right? That's 100 carbons, but you don't have to have that memorized. So when I say it would be wise, it is, change it to, it is imperative, imperative to memorize what I've highlighted in red on table 4.1. The other ones like tridecane, tetradecane, icosane, you don't need to know those. I don't even know if they ever show up in this class. All right, so identifying the longest parent chain. Well, I'm already going to throw a wrench into everybody's plans here, because what happens if your longest chain is cyclic? Well, in that case, you put cyclo ahead, right? And if you go back to the first slide, what was the title of this chapter? It was alkanes and cycloalkanes. So I told you before that if you have 3 carbons in a row, 1, 2, 3, like this, that is called propane. So if you put 3 carbons in a cycle like this, it's cyclopropane. If you have 1, 2, 3, 4 carbons like this is called butane. If they're in a row, okay. If you have them in a ring, 4 carbons in a ring, we call that cyclobutane. And I guess you can see where I'm going. 1, 2, 3, 4, 5. We would call that pentane. And if you have 5 carbons in a ring, that's called cyclopentane. So there you go. And if you're wondering, what if I have 6 carbons? What do you think that would be called? It would be called cyclohexane, right? And we could draw that in if you want. Let's see. A cyclohexane is going to come up a lot in this class. So if you have 6 carbons, this is cyclohexane, probably the most important of all the cyclic compounds, and there's a good reason why it's the most important. Then a cycloheptane, drawing a heptagon. Mr. Dion is not God's gift to drawing heptagons, I can tell you that, but something like that, that would be cycloheptane. All right, there you go. So we go from butane, pentane, hexane, heptane, and then if they're cyclic, we have cyclopropane, cyclobutane, cyclopentane, cyclohexane, and cycloheptane, so on and so on. And if you're wondering, can you have cyclooctane? Of course, it's the same shape as a stop sign, the octagon. Jump in the octagon, right? Anyhow, number 2, we're going to identify and name the substituents after we've identified the longest parent chain. Okay, so I taught you methane, ethane, propane, butane, pentane, hexane, heptane, all that stuff, right? So if you remove a carbon, like let's say you have a CH4 molecule, that's called methane. Okay, if you remove a carbon, you get CH3 attached to something, that's called a methyl. Okay, if you have CH3, I told you that's called ethane. Well, if you remove a carbon, then you have CH3, CH2, and you can have that as a substituent, right? This is an ethyl group here. Okay, That's called an ethyl. So you go from methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, octyl, nonyl, and decyl. I'll be honest that the ones that we're mostly going to focus on, probably 98% of the time, would be these ones: methyl groups, ethyl groups, propyl groups, and butyl groups. Okay, so for example, here we have 2 carbons, so this would be an ethyl group. Ethyl group. Here you have only 1 carbon as a branch, so this would be a methyl group. Here we have 3 carbons in a branch. This would be a propyl group. So propyl, like that. So those are branches, and I'm not going to list them all. We'll have some other slides that show you more information about those. Naming and identifying those substituents. So a ring, right, like the cyclopropane, cyclobutane, cyclopentane, so on and so forth. A ring can either be a parent, okay, it can be the longest chain, okay, because you can't double over a carbon, right? Let's say you had this molecule here, and I said find the longest carbon chain. You can't do this. 1, 2, 3, 4. No, you cannot go from this branch into a ring. Okay, you can't do that. So to find the longest carbon chain here, we have 1, 2, 3, 4, 5, 6, and you can't double over this. You can't go 7, 8. No, you can't do that. Okay, so the longest chain here is 6 carbons in a cyclic structure. So that's a cyclohexane. So you have a propyl group here. So the name of this molecule would be propyl cyclohexane. What if your longest chain is linear like this, and then you have the cyclic one, which is smaller, right? There's only 3 carbons in this ring, but we have a total of 1, 2, 3, 4 carbons in this chain. So in this case, the cyclic portion is the branch or a substituent, and we would call that 1-cyclopropyl butane. So again, a cyclic portion can either be a chain or it can be a branch or substituent, depending on the number of carbons. So when it's got the most carbons, the cyclic part will be the parent. When it's got less carbons than the longest carbon chain, it's considered a substituent. Number 3, we're going to identify and name substituents. Now, if you've got a really complex branch like this one here, we don't see these a lot. There's not a ton of these in our book. There's question 4.13, which covers this. So you want to take a look at question 4.13 in the textbook. But if you have a complex branch like this, there's a total of 5 carbons in here. You start by numbering the longest carbon chain inside that substituent, and you can see that it's got 4 carbons. You start with the carbon attached to the parent chain, so that's this one here. You name the substituent. So if you have 4 carbons in a row, 1, 2, 3, 4, that's called a butyl. And then we have a methyl group on carbon 2. So you call it a 2-methyl-butyl. And then you put it in brackets in the full Iupac name, and then you'll see that in question 4.13. So this whole substituent that's in green here, that would be called a 2-methyl-butyl. 2-methyl-butyl. I'll be honest with you, we don't look at this a lot, okay? Not much. However, it is in the slides, it is in the book in a question, so it is fair game. Now, what you're going to spend most of your time concentrating on between now and the quiz on Chapter 4 would be the common names of substituents, right? I already showed you that if you just have a parent, oops, I didn't mean to do that. If you have a parent, so if you have a parent like this, okay, and if you only have a CH3 attached to it like that, that's called a methyl. There's only one way to arrange that. If you have a parent like this, and if you have CH2, CH3 attached to it like this, okay, that's called an ethyl. And there's only one way to arrange that as well, a methyl and an ethyl. But once you get to a propyl, 3 carbons, there's 2 possible ways to arrange it, okay? You can have it just straight like this, 1, 2, 3, or you can have them branched like this, where you have this carbon with 2 CH3s coming off of it, like this. So here we have a CH, okay, and 2 CH3s coming off, whereas here we have CH2, CH2, CH3. And when we have it like this, we call that an isopropyl. So propyl and isopropyl. This is the Iupac way of doing it here, 1-methyl-ethyl. I don't think I will ever use that with you in class. So you need to know the difference between propyl and an isopropyl group. I repeat, you need to know the difference between a propyl and an isopropyl group. And once we get to 4 carbons, my friend, it gets much more interesting, because if we have just 4 carbons in a row like this, 1, 2, 3, 4, there's actually 4 different ways that we could arrange them. We could arrange them all straight like this as a butyl. We can have them arranged like this, which we call a sec butyl. We can have them arranged like this, which we call an isobutyl. And the last way is a tert butyl. Okay, so you need to know the difference between butyl, sec butyl, isobutyl, and tert butyl. Let me give you some pointers, some little mnemonics that I've developed, or my students have helped me with maybe over the years to help you memorize these. The butyl, I mean, that's just a straight chain, so usually people are pretty good with that one. The isobutyl, if you remember the isopropyl, right? The isopropyl ended up with 2 CH3s on the end, right? Like this. This is isopropyl. So propyl. So an isobutyl does the same thing. It ends up with 2 CH3s on the end, like that. Okay. The tert butyl, I think of tertiary, which means 3, and you have 3 methyl groups, 1, 2, 3 on the end, so that might be helpful. For secondary, right, I think of second, I think of 2, the number 2. So the first carbon that comes off has 2 carbons directly attached to it. You've got this CH3 here, you've got this CH2, you get this CH3 there. So again, whatever you have to use to memorize these, if it's flashcards, if it's just practicing them over and over and over, but you have to know, listen very carefully, you've got to know methyl, ethyl, propyl, explicit propyl. So propyl, you've got to know isopropyl, and you've also got to know butyl, sec butyl, isobutyl, and tert butyl. They come up all the time in organic chemistry. All organic chemistry students who have gone on before you, all who will come after you, have to know these 8 alkyl groups. And if you're wondering, are there more? Absolutely. Once you get to 5 carbons, okay, and I'm not going to ask you to memorize these. You don't have to know these. But if you have 1, 2, 3, 4, 5 carbons, that is called a pentyl. And then you can have an isopentyl, which looks like this, where you have 1, 2, and then you have, so 1, 2, 3, 5, like that. This is called an isopentyl. It's also called an isoamyl. So isoamyl acetate is the smell of bananas. Anyhow, it's neither here nor there. And then you can have a neopentyl or a terpentyl. So if you have something that looks like this is called neopentyl. Okay, I'm not going to ask you to memorize any of those. Okay, I guess the pentyl, you would need to know that, but you don't have to have these ones memorized. The reason I'm throwing them out there is because every class, or almost every class that I teach, not everyone, I suppose, but almost every class, I will always end up with a student in my class who is a real just person who likes to Google everything that we go over and look at secondary sources, maybe look at another website about organic chemistry, or maybe look in another textbook. And so you might see those things in another textbook, or if you watch another lecture from another instructor on the internet, you might hear those terms, and just so you know what they are. All right, so when we're putting everything together, there's some guidelines to follow. Before I get into the guidelines, I have one more thing that I want to mention to you, because I want to stop saying CH3, CH2, and CH2. Okay, let me teach you a little more nomenclature. When you have a CH3, I told you that that's called a methyl, right? If you look at this, that's CH2, this is CH2, this is CH2, this is CH2. Instead of me calling it a CH2, let me tell you what the proper term is. When you have 2 hydrogens bound to bound to a carbon with 2 bonds, that's called a methylene. So a methylene. So we have a methyl, a methylene, and when you have a carbon with only 1 hydrogen and 3 bonds to carbon, so if you have a CH and it's got 3 bonds to carbon like that, we call that a methine with an I. So it's not methine like an alkyl, not with a Y. It's methine with an I. So we go from a methyl, CH3, to a CH2, which is a methylene, and a CH, which is a methine. You can see that methylene is easier to roll off the tongue than CH2. Okay, so there you go. So this would be a methine, this would be a methylene, right? That's the kind of vernacular that I'm going to use with you from now on. All right, so here we go. Here are the guidelines that we use to assemble an Iupac name. So if you've got one substituent present, so here you can see that the longest carbon chain has 7 carbons. 1, 2, 3, 4, 5, 6, 7. Okay, good. So this must be some kind of heptane, right? 7 carbons. We've got one substituent. It's here in the green box. We number that longest parent chain. There's only one correct way to do it, right? There's only one correct way to name these molecules when we're using Iupac rules, okay? And that is, we want to give the substituent the lowest possible number. So that's why we start the number 1 here. So this way we have a 2-methyl group, right? This is a 2-methyl, okay? Whereas if we started numbering over here, then it would be a 6-methyl, and that is incorrect. Okay, we want to give the first substituent the lowest possible number. All right. So I actually kind of misspoke there. When you have one substituent, you give it the lowest possible number. When you have multiple substituents, you give the first substituent the lowest possible number. This is a rule that some students will struggle with. Why? Because they'll try to make it more complicated than it really is. Let me show you what I mean. This is correct over here, right? We have our longest carbon chain. It's got 7 carbons. We've got a methyl group at carbon 2. And we have 2 of them at carbon 5. So the first one is at carbon 2. If you look over here where it's incorrect, the first substituents are both at carbon 3. And then we have another one over at carbon 6. There is somebody usually, or I shouldn't say that. It doesn't happen all the time. But it's got nothing to do with adding up these numbers. Like, let me get an abacus out and start tallying these up. I got 5 and 5 and 2, and I got 3 and 3 and 6. Well, they both give you 12. So it's got nothing to do with adding up numbers. Believe me, organic chemists aren't that smart, okay? All it has to do is this. Whatever the first substituent is, you give it the lowest number, and you just, who cares about the rest? You just give them whatever number they come on, okay? So you look for the first substituent, you give it the lowest possible number, and the rest be damned. Pardon my language, okay? You just go with it. All right? There we go. So if there's a tie, and we always have to give you an example where there's a tie so that you know this rule. If there's a tie, you go for the second one, right? So here you can see that you have the longest carbon chain, okay? Both in the correct one and the incorrect one. There's the longest carbon chain. I know you can identify it, okay? But here you've got methyl groups, one away from the end of both of them. But then you have, so that's all tied, right? So the tiebreaker is this one here. Right, which would be on carbon 3, and so the correct way would be to start over here instead of giving it the number 5. So 2, 3, 6 beats 2, 5, 6. Sometimes I call that a laundry list. I call it a laundry list. Like, I'll list it like this. I'll go 2, 3, 6, and then 2, 5, 6, because I'm not even smart enough to look at it like this. I have to go, that's good. But then I go here, oh, there's my tiebreaker. The 3 wins, so I say this is the correct way. Okay. Anyhow, just something I like to do. Everybody's got to live how they got to live to a certain extent. If there's no tiebreaker, oh boy, this is an annoying one. Look, the longest carbon chain's got 1, 2, 3, 4, 5 carbons, right? 1, 2, 3, 4, 5 carbons. Then here you've got a chloro, here you've got a bromo. You just go by alphabetical order. So since B comes before C in the alphabet, you go with 1 bromo. So let me just mention that. This isn't really mentioned in my slides, spelled out necessarily. But if you have a fluorine as a substituent, it's called a fluoro. If you have a chlorine as a substituent, you can guess, that's called a chloro. If you have a bromine also on this slide, that's called a bromo. And if you have an iodine, that's called an iodo. Okay? And they're alphabetized according to F for fluoro, C for chloro, B for bromo, I for iodo. Let me back up and show you another cool thing about the alphabetization that sometimes annoys students, but it's just the way it is in organic chemistry. So look, we ignore all prefixes when we're alphabetizing substituents except iso, cyclo, and neo. So if you have methyl, ethyl, propyl, and isopropyl, methyl is alphabetized according to the letter M. Ethyl is alphabetized according to the letter E. Propyl is alphabetized according to the letter P. And isopropyl is alphabetized according to the letter I. Notice that there's no hyphen here. It's just isopropyl, all one word. When you get down into the butyls, this is where it gets a little bit of a pain in the butt. Okay, butyl is alphabetized according to the letter B. However, since sec-butyl has this hyphen in it here, we ignore the sec prefix and we alphabetize it according to the letter B. If you have an isobutyl, since there's no hyphen, it's alphabetized according to the letter I. And since you have a tert-butyl with a hyphen in it, you alphabetize it according to the letter B. Cool? So there you go. So those are the letters that you use for alphabetization of your alkyl substituents. And these are the letters that you use to alphabetize your halogens, which are substituents. There you have it, my friends. So when we're naming or numbering the substituents on a cycloalkane, so here the longest carbon chain in both of these is 6 carbons here and 6 carbons there. Well, here you have 2 substituents, so you'd go 1, 1, 3 versus 1, 3, 3. Well, if you make the laundry list, right, 1, 1, 3, and then 1, 3, 3. This one's good. This one, oh, there's the tiebreaker, so this must be the correct way. All right. And then you put it all together in a nice nomenclature sandwich, right? You put the name or the number and the name of each substituent before the chain name in alphabetical order. So, for example, the bromo comes before a chloro, right? An ethyl comes before a propyl. If you use a prefix like di, tri, tetra, penta, whatever, if multiple substituents are identical. So if you had 2 methyl groups, for example, you would say dimethyl, okay? But you don't alphabetize according to that, okay? Because note that any prefix is ignored in organic chemistry except these 3 magic ones, iso, cyclo, and neo. We don't ignore those prefixes. So dimethyl would be alphabetized according to the letter M, for example. Let's say you had a triethyl, okay? Triethyl, which means tri means 3. Okay, you would alphabetize according to the letter E. So di, tri, tetra, penta. You know, after that would come what? Hexa, hepta, octa. We're never going to see those. Okay, past penta. I can't think of an example where we see 6 substituents that are identical in this class. There might be, but they're escaping me at the moment, that's for sure. So here are the rules. And if you're wondering, you know, oh man, there's so many rules. Well, again, anybody who studies organic chemistry, if you have any friends who have taken this class at another college or university, they're always going to have to learn these rules. Everybody does. And you know what the good news is? Let me tell you some really good news about nomenclature. If you can understand this and you can apply this for Chapter 4 and for your quiz in Chapter 4 and for your practice problems in Chapter 4, the good news, great news is this. These rules are going to help you in the nomenclature of alkenes. They're going to help you in the nomenclature of alkynes. They're going to help you in the nomenclature of alcohols, aldehydes, whatever nomenclature we look at for the rest of Organic Chemistry 1 and Organic Chemistry 2. These are the fundamental rules, and you will use them every time nomenclature comes up. So it is not in vain, and it's not just a one-time deal. It is for the rest of the class. So what were the rules? First of all, you identify the longest carbon chain, whether it's linear or cyclic. You identify and name the substituents, you know, a chloro, a bromo, a methyl, an ethyl, a propyl, an isopropyl, a tert-butyl, a sec-butyl, an isobutyl, a butyl, whatever, right? You number the parent chain and you assign a locant. A locant is nothing more than a number to each substituent. So say like 1, you know, or 2 methyl, you know, 3 ethyl, things like that. You list the numbered substituents before the parent name in alphabetical order. There's one more rule that I want to mention on here, is that if you have letters and numbers, so letters and numbers are separated by a dash, okay? Whereas if you have numbers and numbers in a name, they're separated by a comma. Okay, and if you have letters and letters, they're not separated by anything. All right, so here we go. I don't know when we start with this compound, but anyhow, that's what's in my slides. So the longest carbon chain here, and you know, when you just start out in nomenclature, and I do this all the time, I'll write down everything I know, okay? Just, it really is handy. So the longest carbon chain here has 6 carbons. 1, 2, 3, 4, 5, 6. Now, where are we going to start numbering this compound? Well, we're going to start we're going to start down here, because if this is carbon 1, 2, 3, and 4, we have substituents at 1, 1, 3, and 4. Right? I'm going to erase those numbers, and you don't have to do that. But let's say you did it incorrectly, right? If you numbered it like this, 1, 2, 3, 4. In that case, you'd have a substituent at carbon 1, another one at 2, and then you'd have 2 at carbon 4. So this looks good, but here you go. Oh. You know, 1 is a lower number than 2. And so the red numbers, the ones that I had first, were correct. Okay, so we go 1, 2, 3, 4, like that. And if you want to put 5, 6, be my guest, but you don't need those because there's no substituents on there. So what are the substituents that we have? At carbon number 4, we have a tert-butyl group, so 4-tert-butyl. At carbon number 3, we have an ethyl group, so 3-ethyl. And at carbon number 1, we have 2 methyls. So instead of saying 1 methyl and 1 methyl, we say 1,1-dimethyl. Remember I told you that numbers and numbers are separated by a comma, and numbers and letters are always separated by a hyphen. Okay, so if we put this all together in a beautiful nomenclature sandwich, cyclohexane is going to be the last thing because it's our parent, cyclohexane. Then if you alphabetize the substituent, tert-butyl is alphabetized according to the letter B, ethyl is alphabetized according to the letter E, and dimethyl is alphabetized according to the letter M. Remember, we ignore prefixes like tert and di when we're alphabetizing. The only prefixes we don't ignore are iso, cyclo, and neo. Okay, and you're probably never even going to see neo in this class. So there we go. And if you're wondering, you know, why didn't you put cyclo? Why didn't you alphabetize that according to the letter C? Because it is the parent. The parent always comes last. It's only the substituents that you have to put in alphabetical order. So if I put all this together, I've got 4 tert-butyl, 1 3-ethyl. I do know the alphabet. 3-ethyl. Sorry, I'm thinking about too many things at once here, I think. And then I've got 1, 1. Oh, it's not going to fit. 1, 1-dimethyl. 1, 1-dimethyl cyclohexane. So let me move all this over a little bit. There you go. And there's the name of your compound. So it's long, isn't it? 4-tert-butyl, 3-ethyl, 1, 1-dimethyl cyclohexane. But again, what's so great about this is that it allows scientists to communicate with one another. You know, if you made this molecule and you wanted to talk to somebody in another country about it, right? If they've learned the exact same rules for nomenclature as you, they're going to know exactly what you're talking about. You don't have to draw them a picture of it. You just tell them the name. Hey, I made some 4-tert-butyl, 3-ethyl, 1, 1-dimethyl cyclohexane. Yes. Okay, good. What did you do with it? I don't know. I converted it into a block-busting drug, right? Okay, so with that in mind, let's try and provide some systematic names for these compounds. They might seem intimidating when you first look at them, you know, especially because they have these cyclohexanes in them. But let's give them the old college try. Could anybody tell me what the longest carbon chain in B would be? And it is not a trick. I'm not trying to trip you up or anything. What the longest carbon chain be here? Yeah, absolutely. All my students are killing it. Yep. It's the cyclohexane, isn't it? You're all correct. Okay. All my students were like cyclo or cyclohexane, and they're all 100% correct. Well, look, if the longest carbon chain is 6 carbons in a ring, you're right. The parent must be cyclohexane. So let's put that in here, cyclohexane. Wow, that was really fast. Good work. I've only got one substituent. It's this whole thing right here. It's on 1 carbon. So in this case, I don't have to say it's 1 substituted since there's only 1 substituent anyway. It would be redundant to do that. Now, this might not be as easy, but there's only 4 carbons in this substituent, right? There's 1, 2, 3, 4. So could anybody identify this as being a butyl, sec-butyl, isobutyl, or tert-butyl? Yes, Jessica got it. It's the sec-butyl group, isn't it? Right, so if we want to put this all together, so this is a sec-butyl. Remember I told you that off of the first carbon, you've got 1, 2. So I think secondary or 2. I don't know. And yeah, it's just my way of thinking. So we put that all together and we get sec-butyl cyclohexane. There you go, my friends. So we put that all together to make it look a little cleaner. Sec-butyl cyclohexane. That's it. There you go. You've named your first organic compound, and it didn't take us all that long. Now, the next one is 4.8F. I'm going to give you a second. Could anybody identify, or could anybody tell me how many carbons are in the longest chain in this one? In this one here. And it might take you a second to look at it and figure it out. Cha, okay, maybe you guys are faster than me, okay. Yeah, all my students are correct. It's 8 carbons. You guys are really fast, that's great, okay. I'm not a speed guy, but I don't time myself when I do, organic chemistry, but yes, you're all correct. It's 8 carbons, and I guess you all found that the same way, which was good old-fashioned trial and error. Now look, when it comes to numbering this, look, do I start over here? Is number 1 here, or is number 1 over here? And I know that I'm sure a lot of you know the answer already, but let's see if we started numbering over here on the left-hand side. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's 8 carbons. So this is some kind of octane. We have substituents at carbons 3, 4, 5, and 7. If I was to start numbering on the other end, so let me just try and erase all this without erasing the longest carbon chain, which I don't think I can. All right, let's fix it. There we go. We'd have 1, 2, 3, 4, 5, 6, 7, 8. So then we'd have substituents at carbons 2, 4, 5, and 6. Can anybody tell me which way is correct, the way in blue or the way in red? There you go. It's the way in blue, isn't it, right? Because we have our tiebreaker here. So this is the correct way. Correct. And this is incorrect. So a student asked me, could the parent chain begin on the carbon attached to a cyclohexane? No, because that's considered a substituent. So what the student is asking is, could you call this carbon number 1 over here? No, because that's not part of the longest chain, right? The only way that that could be carbon number 1 would be if the cyclohexane was the longest carbon chain in the molecule, right? So you have to start over here as carbon number 1. So there you go. So it's the blue way. Let's see if we can list all these substituents. There's a bunch of them. I'm kind of running out of space here. Let me just find the space here, Gene. So we've got a 2-cyclohexyl, right? If you've got, cyclohexyl, cyclopropyl, cyclobutyl, cyclopentyl, so on and so forth. What else? My students are spitting it out here at me. We've got a 5,6-dimethyl, yes. 5,6-dimethyl, absolutely. 5,6-dimethyl. I can go to the chat and read what you guys are putting in there. A 4-ethyl, yep. Students are faster than me. There you go. And that's it. That's everything. And now we need to put it together in a beautiful nomenclature sandwich. So we got cyclohexyl. We alphabetize according to the letter C. Dimethyl. Remember, we ignore prefixes except for iso, cyclo, and neo. So we alphabetize according to the letter M and then E. So the 2-cyclohexyl comes first. Let me get my red pen. So this is 2-cyclohexyl, 4-ethyl, 5, 6. I'm running out of space again, aren't I? 5,6-dimethyl. Oh, long names. 5,6-dimethyl octane. So there you go. There you go. So you just named yourself a beautiful organic compound. You know what's fun to do now that you're learning a little bit of nomenclature? And this is something that I'll do with you one day before class. Is we'll look at the structure of some of the most common marketed drugs, or drugs that are the highest in terms of, or highest volume in terms of sales, blockbusting drugs. And it's fun to look at the structure of all kinds of prescription medications that you've all heard of or seen on the news or seen on TV in commercials or something, to not only identify their functional groups, but now that you've studied a little bit of organic chemistry and you know functional groups, if you're interested in any, prescription drugs or illegal drugs or just any kind of drug and you want to look it up its structure, let's say on Wikipedia, which you can do, you're going to start to recognize functional groups immediately. And you'll notice that drugs will always have three types of names. They'll always have an Iupac name. Okay, they'll always have just a systematic Iupac name, which nobody uses, but then they'll have a generic name and then they'll have a trade name. So I'll let you take a look at that in your own time, but it's just something to, a little food for thought and kind of an interesting, something interesting for you to think about. All right. Well, that's a couple of practice problems. Let me show you something that's even crazier, and that is naming bicyclic compounds. And when I say crazy, I mean crazy fun, because it is very doable, but really interesting to learn how to name bicyclic compounds. So a bicyclic compound, what is it? It's when you've got two fused rings. If you look at this molecule on the left-hand side, you see you've got 6 carbons in a ring here, but you also have another ring, right, that's got 5 carbons in it. And it doesn't matter if you slice it that way or if you look at it this way, you've got 5 carbons in a ring. So this, what's drawn over here on the left-hand side, is the same thing as this. It's just another way of viewing it. I can't even make a bicyclic model with my model kit. Okay, we break the models. I actually have another model kit somewhere in the closet here that I maybe could, but I have never tried. But anyhow, these are a bridged or a bicyclic compound. And if you go back to that structure of morphine, did we have the structure of morphine? Yeah. You can see that in the structure of morphine, you see there's a 6-membered ring right here. Well, there's another ring there, isn't there, right? There's a bridge going over here, right? You have 1, 2, 3 carbons, and then it goes over this nitrogen and up on this bridge right there. Imagine trying to make that. Not simple, but interesting, definitely cool. All right, so let's go back to naming bicyclic compounds and how you would name this compound. Like, what the heck is the name of this? Okay, so in order to name a bicyclic compound, we put the prefix bicyclo in front of the parent name. Let me show you how to name this particular one here. So you count up the total number of carbons. So can anybody tell me the total number of carbons in this molecule? And it's not a trick. How many total carbons are in here? How many total carbons are in that molecule? Yeah, exactly. Exactly. There's 7 carbons, aren't there? Right? If you number them, and we'll start here, we have 1, 2, 3, 4, 5, 6, and then you have 1 up here. That's 7. Okay? These positions right here, where the junction of the 2 rings are, we call those bridgehead carbons. So we call these bridgehead carbons. Why do we call them? Because that's where the bridge is, right? That's the bridge right there over the top. Okay, so now that we've identified bridgehead carbons, and I'm just going to erase that for now, erase the little arrow. So bridgehead carbons, the way that you would name this compound is that this is some kind of bicyclo. Then you put a square bracket, close it, bicycloheptane. Why? Because it's got a total of 7 carbons. So what you put inside these square brackets, was that the eraser? No. So what you put inside those square brackets is always 3 numbers. Okay, there's always 3 numbers. We could call them whatever we want. We could call them X, Y, and Z, but you have to come up with those numbers. So what you do is, after you've identified the bridgehead carbons, which I have highlighted in yellow, is you count the number of carbons in each bridge outside of the bridgehead carbon. So we have 2 carbons here. We have 2 carbons here. And how many carbons are in the last bridge? And it's not a trick. How many carbons in the last bridge? So we have 2 carbons in one of them. Yeah, there's just 1. So the way that you number it is you start with the biggest number and you go to the smallest number. So this would be bicyclo 2.2.1 heptane. Up here I put commas. I shouldn't have done that. I should have put periods. So you put a period in between the three numbers. So the name of this compound, whether you draw it either one of these ways, would be bicyclo 2,2,1 heptane. All right, there you go. So that's the crux of how you name these types of compounds. However, it gets a little more complicated when the bridges are all different sizes and when you have substituents. So the first thing you probably notice is that when the bridges are different sizes, the smallest, it goes largest to smallest, right? So largest bridge count, so largest to smallest, right? And since two of them had 2 carbons, we just went 2, 2, okay? But you always start numbering at a bridgehead carbon. So let's take a look at an example here. It says to number the bicyclo parent, you always start at a bridgehead carbon, right? Here are the bridgehead carbons, these ones here, okay? And you number the longest carbon chain connectors first. So look, I've got 3 carbons in this connector to the bridges, to the bridgehead carbons. I've got 2 here, and I've got 1 here. So you number the longest chain first, which is the green one. It's got 3 carbons. Then you'd go to the 2 carbon chain, which is the one circled in blue. Then you go to the 1 carbon, connector, I guess, which is the one circled in red, only has 1 carbon. So get me on that? Now, the next thing you want to do is it says without violating that first rule, you give the substituents the lowest possible number. So these 2 molecules are identical. But remember, if you want to communicate with a scientist in another country, another state, another town, another city, whatever, there's only one correct way to name the molecule. Okay, you can't just be like, I'm naming it Joe. I'm going to call, can't do that. We've got to give it an unequivocal name. So if you look at these 2 molecules, okay, they're both bicyclooctanes, aren't they? Right? Well, they're the same molecule. So it's a bicyclooctane because there's a total of 8 carbons in the bicyclic structure. But there is this methyl group hanging off here. Now remember, we have to start on a bridgehead carbon. There are 2 bridgehead carbons. You could either start here or you could start here. The correct way, watch, you go from 1 to 2 to 3 to 4. You have to keep going in a straight line to 5 to 6 to 7. Why do you go from there to there? Because this is the longest chain, or the longest connector. This is the second longest connector. Then you go up to the shortest connector. So this is correct, going from 1 to 2, 3, 4, 5, 6, 7, 8. So this is a 6-methyl, right? So 6-methyl would be correct here, 6-methyl. Okay? The reason this way is incorrect, the person correctly identified the bridgehead carbons. There's one here and there's one here. They went through the longest chain first, right? They went 1, 2, 3, 4, 5. Then they went to the second longest chain, 6, 7. But the problem is a 7-methyl is higher than a 6-methyl, so they started at the wrong bridgehead carbon. You always number it in such a way that you give the first substituent the lowest possible number. There you go. All right, with that in mind, let's try and name that compound. You know what, before we do that, why don't we try to finish naming this compound? So delete. So we have a 6-methyl. Let's write down what we know. This is a 6-methyl. It is a bicyclooctane, right? Because there's a total of 8 carbons. Could anybody tell me what the numbers are for the bridges? And it's not a trick. So the number of carbons in the actual bridges. Yeah, it's 3, 2, 1, right? Because in the first bridge, we have a total of, you don't count the bridgehead carbons. You leave those out. They're not the connectors, right? You've got 3 carbons in this connector, so 3. Then you've got 2 carbons in this connector, 2. And then you've got 1 carbon in this connector, so it's 3, 2, 1. So you put this all together, and the name of this molecule would be 6-methyl took the L there, didn't I? 6-methyl, 3-2-1, 3-2-1, and then bicyclooctane. There we go, bicyclooctane. So a student asked, why would it not be a 2-methyl? Okay, I'm just going to move this out of the way so I have a little more room to explain stuff here. So that's the name of that compound. Why wouldn't this be a 2-methyl? So let me just delete all this. Because the rule states, like if you redraw this compound, it's not my best artwork here. Do it like that, and I'll fix this bond. There you go, something like that. Why isn't this a 2-methyl? Right? Like, why aren't you going like this? 1, 2. Because you started a bridgehead carbon, that's correct, but you have to go through the longest connector first. Right? You do not add a period after the third one. All right. With all that in mind, let's see if we can name a bicyclic compound. You put a tricky one in here from the get-go. Let's name a simpler one, maybe. Let me think of one. What if we had to name something like this? So just ignore this one for now, and we're going to try doing something different. Let's try this. What if I had a 6-membered ring like this, and then I had a bridge like that? It's not very big the way I drew it, but how many total carbons are in this structure? Could anybody tell me? Yeah, there's 7 carbons. So this is some kind of bicycloheptane, right? So this is a bicycloheptane. There's no substituents on it, so I've actually made this one maybe too easy. But we're going to take this part, the bicyclo part, separate it like this, and then we're going to number the bridges. So I've got 2 1-carbon bridges, and then I've got 1 3-carbon bridge. So it's going to be 3, 1, 1. So it's bicyclo 3, 1, 1 heptane. Maybe that example's too easy. I don't know. Anyhow, you get the idea. Let's erase this. Let's try the one that's here. Delete. Okay. So this is a bicyclic compound, isn't it? Right? You've got a ring here, and you get another ring fused to it. Okay. So the bridgehead carbons would be this one and this one. I start at either this one is carbon number 1 or this one at carbon number 1. If I label the other one in green, could anybody tell me which one? Sorry, I meant to put the number 1 in green. Which number 1 would I? Which one would I start with? The one in green or the one in red? Yeah, the one in green. Absolutely. Right? Why? Because if I went with the one in red, then I'd have 1, 2, 3, 4, 5, just like that. So then you've got 2 and 5, 5. Whereas if you go the way in green, come on, you go this way, 1, 2, 3, 4, 5. Then you've got 2, 2, 5. So 2, 2, 5 beats 2, 5, 5, right? 2, 2, 5 versus 2, 5, 5. Right? So this is the tiebreaker. And so the way that we have it here is correct. So then we go 6. Then we go to the next longest bridge, 7, 8. So we've got 4 methyl groups here. We've got a methyl group at carbons, or 2 of them at carbon 2. We've got 1 at carbon 5 and 1 at carbon 7. So we've got a 2, 2, 5, 7, 2, 2, 5, 7 tetra methyl. That's a lot of methyl groups in the compound. There we go. And then we just have to identify how many total carbons So we have to identify how many total carbons are in the bicyclic portion of the molecule. So there's a total of 8 carbons in there. So this is some kind of bicyclooctane. So we'll put this all together. Let me move this down here. Let's put this down here, 2, 2, 5, 7. And then we'll put bicyclo, put our brackets, octane. Could anybody identify how long is the longest bridge? Yeah, there's 4 carbons in the longest bridge. 1, 2, 3, 4, like this. So we'll put a 4. How many carbons are in the second longest bridge? Right, there's 2 in the next one. So 2 here. So we have a 4. Then we have a 2. And in the last bridge, there's none. Okay, there's 0, right? If these are the 2 bridgehead carbons, you've got 4 carbons here, you've got 2 carbons here, and that's it. There's no other bridge, right? So the last number is a 0, like that. So that's the name of the compound. It's 2257 tetramethyl bicyclo 420 octane. And there you have it. You've named a few bicyclic compounds.